Hi everyone, I'm Adval Jyotiside. I'm going to teach about the state space modeling today. So this is going to be the first lecture in state space modeling. Okay, so to understand the state space modeling, I have just taken a very well-known mechanical system. This is nothing but a spring balance, or you can call it as a mass, spring, and damper system, where a force is applied at this mass and this mass is subjected to a displacement of x of t. And we all know how to model this system, and this is the differential equation representing the system. And we are very familiar with this transfer function modeling. So if you apply the Laplace transformation and separate the input and output variables, we are going to get this transfer function model. Of course, in this transfer function model, the output what we have taken is x of s, otherwise the displacement. But if you really look at the system, the output variable need not be x of t, it can be the velocity, I mean the v of t also. Am I right? So when this mass is moving, it will have a displacement variation with respect to time, and also the velocity also will vary with respect to time. Therefore, the variables associated with the system is not just displacement, it can be the velocity also. So if I am going to take the velocity as the output, how should I represent the system? So this is what is going to be this model of the system. See, f of t is equal to m into this d square x by dt square is d by dt of dx by dt. That dx by dt is nothing but the velocity that I have taken as dv by dt. And of course, dx by dt is bv. And if you want to get x from velocity, you have to integrate velocity with respect to time, k into this displacement, which is obtained from the velocity as an integration of velocity. So again, if I just take the Laplace transform, I am going to get this. From this, I can get this transfer function as v of s by f of s is equal to this. You are very well able to see the denominator remains the same. That's okay. So anyhow, so if I want to study about the displacement, I have to take this model, this transfer function model. Or if I want to talk about or study about the velocity, I have to take this transfer function model. What if I want to have these two variables in a single equation? Whether that is possible in transfer function model, it is not possible. This is one of the main drawback of transfer function model. Okay, so for a single input or multiple inputs, if I am interested in multiple outputs, for in this case, if I am interested in multiple outputs of x of t, the displacement as well as the velocity, I cannot bring in both these outputs into a single transfer function model. Okay, so this is the major drawback with this transfer function model. Okay, so and other thing is, when we define the transfer function, how we define is the Laplace transform of the output, the ratio of the Laplace transform of the output to the Laplace transform of the input. The important condition is the initial conditions should be 0. But that may not be true in all cases. For example, if you take an electrical circuits, of course the capacitors can have initial charge, and therefore it can have some initial conditions. And if you take a nonlinear systems, mostly the case is very true that initial conditions will exist. So this transfer function model has got that drawback also. That is, if you want to analyze a system with initial conditions, you cannot do that. Okay. So another problem with this states transfer function modeling is, see, this is a second order system. We are able to see what are the variables, but if you go for a multiple or higher order systems, uh, there will be many variables changing within the system when an input is applied. But your transfer function model will relate only this one of the variables which is considered as an output to this input. So what happens to these variables, other variables related to the system? Okay, so for example, if you take an electromechanical system, so we are all familiar, maybe a electrical motor connected to a load. What is the input? Input is the voltage and output is the angular displacement. But in that system, whether the angular displacement of the shaft of the rotor alone is varying with respect to time? No. In an electrical system, currents will vary with respect to time. The angular velocity will vary with respect to time. So, what if we want to analyze all these variables together, how they are going to change with respect to time? Okay, that is not possible in this transfer function model. So these are some of the main drawbacks of this transfer function model. And of course, it has got various advantages. We will be, particularly in frequency domain and all, but still this suffers these kinds of drawbacks. So we are going for some other model, which is known as state space model or state variable model. You can call it as a state variable model or a state space model. Okay, so we'll just see about the state space model, taking this mechanical system as an example. First of all, understand that in transfer function model, we are transforming the time domain equation to Laplace domain. Okay, so that is how we get this transfer function model. But in state space model, we will remain in the time domain itself. So we will remain in this time domain itself and we will just bring in all the variables which are going to change with respect to time. Okay. So if you take this mechanical system itself, what are the variables that change with respect to time in this? Of course, if the displacement varies with respect to time, the velocity is also going to vary with respect to time. And if velocity is going to vary with respect to time, acceleration is also going to vary with respect to time. Okay. So therefore, the variables associated with this system are x of t, v of t, and a of t. But the question is whether I need to consider all these variables associated with the system. Okay, that's the question. See, whether I should take x of t, whether I should take x of t, v of t, and a of t, or is it just necessary to take x of t and v of t? You will be able to see that if I know x of t and v of t, x of t and v of t, this acceleration can be found out easily. For example, see, the variables associated with the system are x of t, v of t, which is given by dx of t by dt, and a of t, acceleration, is nothing but d square x of t by dt square. Okay. So among these variables which change with respect to time, if I know this dx by dt and x, I can find out d square x by dt square. For example, d square x by dt square is equal to f of t minus f of t by m and minus b by m dx of t by dt minus k by m x of t, isn't it? So if I know x of t, the solution, otherwise x of t, and if I know dx of t by dt, immediately I can, with the help of, if I know this input also, I can find out d square x of t by dt square, which is nothing but the acceleration. Okay, so it is very obvious that these two are the minimal set of variables I need to describe this entire system. Okay, but at least I need x of t and dx of t. Dx of t by dt, that is nothing but the v of t, that velocity. So these two variables, I am going to call them as state variables, because these two variables define the state of the system for any time. If I want to understand the behavior of the system for any time t, it is just enough to know these two variables, x of t and v of t. So these two variables, I am going to call them as state variables. Okay. So usually the state variables in state space modeling are given the notations x1, x1 of t and x2 of t. Alright. So x1 of t is x of t and x2 of t is nothing but dx of t by dt. So these are the state variables which I define for the system. Okay, so if you look at the system, I can relate, the state variables to the system, physical system also. There is easy way to identify the state variables. The state variables I have to choose. Usually the state variables are associated with the energy storage elements in the system. So what are the energy storage elements in the system? The energy storage elements in the system are the spring and the mass. What is the energy associated with a mass? The kinetic energy, you all know, it is half mv square. So instantaneous energy is, if I take v of t. And what is the energy stored in a spring? It is half k x square or x of t square. So the variables associated with this energy storage elements are v of t and x of t. So that gives me a clue that I can choose x of t and v of t as the state variables. So again, so how do I define that state variables now? So the state variables I can define as the minimal set of variables, time dependent variables, minimum set of time dependent variables, with the help of which and the knowledge of the input I can find out, or I can define the behavior of the entire system. I can define the behavior of the entire system. So obviously here x of t and v of t are the state variables which I am able to relate to this energy storage elements also. Okay, right. So the concept of state variables should be clear, I believe. Now I am going to talk about something called the state. So these are state variables, and let me define what is meant by a state. State is a set of, usually the state is represented by x, capital X we use. X of t is a set of all the state variables. In this case, the state is x of t and v of t. or you can say that x of t and x dot of t. Anyway, in all these ways you can denote. Okay, so the set of all these state variables is what we call it as a state. Why? Because that talks about the state. This set, this entire values, the values of all these state variables at a particular time t gives me the state of that system at that particular time t. Okay. Then there is something called state space. State space. State space is a vector space with the state variables as the axis. I have a vector space. So here there are two state variables and therefore it is going to be a two-dimensional vector space. So in this vector space, in one axis I am going to take it as x1 of t and the other axis I am going to take x2 of t. So therefore this is a two-dimensional system I can call, because the dimension of this vector space is 2 and this vector space I am going to call it as a state space. Okay, so this state space, in this state space I can mark the value of x1 of t and x2 of t at any time. Okay, so maybe when the system is going to oscillate, or when the system is going to, when the system is subjected to an input f of t, this x1 of t, x of t and v of t is going to vary with respect to time, and at each and every time t, if I take the corresponding values of x1 of t and x2 of t, I can just plot it in this vector space. I'll get something called trajectory and all that you can study in detail. Okay, so anyhow, this is what we call it as a vector state space. And the analysis of the system within the state space is what we call it as state space analysis. State space analysis. So I have introduced you to some concepts of state variables. First we saw what are the problems with this transfer function model. Why we need to go for another alternate model, and that is nothing but the state space model. So please understand that state space model is in the time domain itself, and we understood what is meant by state variables. It's a minimal set of variables that is necessary to describe the system, and with the help of the state variables and the input of the system, we'll be able to define this performance of the system for any time t. Okay, then we understood what is meant by state. Then what is meant by state space. Okay, so now let us try to understand what is meant by state space equation. Okay, so state space equation. Please remember, the state space variables can be identified from the energy storage elements present in the system. Okay, so already we have defined the state variables as x1 is equal to x of t and x2 is equal to v of t, that is nothing but dx of t by dt. Okay, so now state equations are nothing but those equations which describe the variation of the variation of these state variables with respect to time. Okay, so what are the state variables? Obviously x1 and x2. Okay, so what are the terms that describe how this state variables varies with respect to time? dx1 of t by dt, and another state variable is dx2 of t by dt. Okay, so these two terms explain or describes how these state variables x1 of t and x2 of t varies with respect to time. Okay, so this variation has to be given by an equation. Please understand about the state equations. The state variables we have already defined, and we are going to describe with some equations which are going to describe the variation of the state variables x1 of t and x2 of t with respect to time. These equations are what I am going to call it as the state equation. Okay. So obviously dx1 of t by dt is already available. It is nothing but x2. So we got one state equation directly. Fine. Now I have to get the other state equation. So I'll just make use of this differential equation. You can make use of the differential equations of the model system to get the other state equations. Okay. So if what I can do is this, I'll rewrite this equation as f of t is equal to m. So this is d square x by dt square. This d square x by dt square is d square x1 by dt square. dx1 by dt is nothing but what? X dot. Otherwise dx2 by dt. So I can write it as dx2 by dt. Okay. Plus, what is this? b dx1 by dt is nothing but x2. This is x1. K x1. So from this I will get this dx2 by dt. What is this dx2 by dt? So I can get from this as minus, I will write the x1 terms first, k1 by m into x1 minus, then I will write the x2 term, b by m x2 minus 1 by m f of t. See, I got the state equations representing the system. Okay. So is it okay if I write this state equation in a matrix form? I think I can very well write these state equations in a matrix form. So I'll just remove this these lines which may not be necessary now. Right, from this state equations, I'm going to get another matrix equation. So here I will put this dx1 of t by dt as x1 dot for the sake of simplicity, and this is x2 dot. Okay. So I'll write this equation as x1 dot x2 dot is equal to, first equation I'll put it in a matrix, x1 x2. So this equation doesn't have x1, it has only x2 and its coefficient is 1. So I'll put 0 1 here. And what about this equation? This is x1 is minus k1 by m, and this is minus b by m. Okay. And this does not have any other term, but this has got a term associated with the input. So since there is only one input, I will put it as f of t. Okay, so the first term doesn't have any f of t, it is 0. The second equation has got minus 1 by m as f of t's coefficient. I'll put this. Alright, so now I can remove this. So though I had two state equations, I've just represented that as a single matrix equation. Now I will call this as the state equation. Simplified state equation in matrix form. But this state equation does not explain anything about the output. It talks about how the states vary with respect to time. Okay. What about the output? As I started in my lecture, the output for the system can be either displacement or the velocity. Okay. So if let me say I'm interested in taking this x of t as the output. Usually in state space modeling, output is defined by y of t. The notation used is y of t. Let me say I'm interested in taking this output as the displacement, therefore x of t, or in terms of state variables, I can write it as x1 of t. Am I right? X of t is x1 of t. Okay. So this output equation also I can write in terms of a matrix equation. So I will write y of t is equal to, I will write it as the same vectors I will bring in here, x1 and x2. So this is 1, 0. That's it. Okay. So this is the state equation. Now this is the output equation. Let me say I'm interested in output as so here I have taken the displacement as the output. So now I'm going to take the velocity as the output. Velocity as the output. Okay. So in that case, what is y of t? Velocity. Velocity is nothing but dx of t by dt. What is dx of t by, in terms of state variables, it is nothing but x2. So shall I write it as in matrix form? Y of t is equal to x2, right? 0, 1, x1, x2. Amazing. So now this is my output equation. Okay. Now let me say I'm just interested in taking output as the acceleration. If I'm taking out output as acceleration, how do you get output as an acceleration? Y of t is equal to d square x of t by dt square. That is, I can get it from the original equation as minus b by, so yeah, first let me write the x1 term minus k by m x1 minus b by m x2 plus 1 by m f of t. Okay. So what is it? Y of t, I can write it as x1 minus k by m minus b by m into x1 x2 plus 1 by m f of t. See? I got one matrix, row matrix, as a vector, written as a product of the state vector, okay, and this, okay, right. So now this is the state equation, these are the output equation, and this output equation varies depending upon which variable you are going to take it as an output. Okay, so I'll take an acceleration as an output and I'll write it here. So for my study, I'm interested in taking this acceleration as the output. So this acceleration as the output, I will write it as y of t is equal to minus k by m minus b by m into x1, x2, okay, plus 1 by m. I think this, sorry, this minus this f of t, okay. So these two equations together is what we usually call it as the state space model for this system, taking this y of t, otherwise the acceleration, as the output. If you model any system, ultimately you are going to get a system of this kind, okay. So therefore we give a standard form to the state space model, that is nothing but x dot is equal to ax plus bu and y is equal to cx plus du. Okay, this is the standard form for the state space model. So obviously this is the state vector we call. Okay, this x represents the state vector. State vector is nothing but a vector containing all the state variables, and this matrix, this matrix, A matrix, we call it as an A matrix or a state matrix. State matrix, and this U is the input vector. Okay, and this B matrix is what we call it as the input matrix. Input matrix, and this is the output matrix. Okay, and this is the output vector. Of course, here we have got only one term, but there may be more outputs I can take. Okay, and this is called feed forward matrix. Okay. Please note that I can take more than one output also. For example, I may consider the velocity as one input, one output, and the acceleration or the displacement or something else as the another output. In that case, I will put y1 of t as the acceleration. Let me take it as acceleration, and if it is okay, so let me take it as y1, and y2 of t I will take it as a displacement. In that case, displacement is x1 directly, right? So I can always replace this as x1. So displacement is x1, therefore I will put 1 here and I will put 0 here. So y1 is the acceleration, that is the first output, and the second output is the displacement. Okay, so I can take even the velocity as another output, and I can put 0, 1 here, so that velocity is equal to x2. I can just put anyway. Okay, so therefore, even though you will be able to clearly say that this output is going to be a vector, and this vector is an output vector, and of course this is going to be a matrix, output matrix, and this is the feed forward matrix, and this is the input vector. Okay, so we just got this state space model describing the system, taking this acceleration and the velocity, the displacement as the output. Okay. So state matrix here is this, the B matrix here is this, and the C matrix is this, and D is a matrix this. You'll wonder whether this is a matrix. So there can be more than one inputs. Okay. So but here in this case there are only one input. Assume that there are two inputs in the system, and therefore you will have F1 and F2 probably. In that case you will have another columns, and we will see such cases in the later classes. So the first lecture is over, and here I have explained about the state space model of the mechanical system, and in the next lecture we will just describe about the state space model of an electrical system. Thank you.